Okay, so we'll look at one last example, which is pretty interesting, and I think I motivated that already. If I have a ceiling, right, I tie a block of wood over here, and I shoot a bullet, right? I shoot a bullet directly to the wood, right? And then this will absorb the bullet, and so it absorbs the bullet, and the whole box will get sort of swung because of the momentum being hit here to a given height. Okay, so I want to find out what's the height, right? Can I find a general relationship? If I give the v, can I find the h? Okay, so this is going to be combining the conservation of momentum and conservation of energy together in a combined example, and it's also a multi-step example. Okay, so I'll show you how to approach this. So remember, with so that's our aim, that's what's given, right? So with conservation of momentum, you want to split into before and after. Now this is a multi-step example, right? There's a couple of things happening, so draw out all the key steps. Maybe there is, remember the roller coaster example in one of the example, we have this point, we have this point of interest, we have this point of interest with this point of interest. So draw 1, 2, 3, 4, and then you can do conservation of energy at each point, right? So we're going to do that over here as well. But we'll draw out the instance of time. This time it's not so easy to combine with one diagram, so draw out. So this is step 1, is when this initial velocity shooting over here, and the block is still, right? Step 2 is when what's the second key step that's happening in this physical example, is when the bullet gets collide with it, right? So now it's absorbed to it, and it's the whole thing moves at some velocity. Okay, what's the problem here? Immediately I see that I'm repeating variables, so a bad habit like that. So I'll change that in a second, but let me finish the diagram first. But make sure when you do this to remember to change these variables. So now this guy is going to get, the bullet's going to get lodged into the wood, right? And it's going to, so this was the original height, like this. So I'll just say the center of height, center of mass of this to the center of mass of this is the height difference. Okay, that this guy has moved. I'll draw it over this side. Just so I can save a little bit more space for my steps over here. Okay, so these are the 3 key steps. So let's give things names. Okay, so let's say this is the initial velocity of the bullet. Okay, so UB, and what happens over here? Then the mass of the bullet has MB, and there's the block over here. So we have a mass. Okay, the mass of the block MB. Well, that's just not going to work, does it? Box? No. Wood. All right, let's go with that. So be careful. Sometimes you have to be a bit creative when solving. Who says physics is not a creative subject, right? So you have to be a bit creative in what variables you use. And now they're lodged together, right? So you have M bullet and M wood together. Is it fine to call that V? Yeah, let's call that V. Yeah, V combined. Just to be clear, right? V combined, and I'll call that height over there, and that seems to be fine to me. Okay. In case I need this angle, I'll define this as well. The maximum angle it'll go to, right? Sometimes don't shy away from writing a couple of things, a couple of words more, just to be clear. Write it in full if you want, combined. But then in the equation, what I usually do is, if I label something with a long subscript, a very descriptive subscript here, later on I'll abbreviate to VC, and I make sure it doesn't collide or contradict with any overlap with any other symbols that I have defined. Okay, and that's usually fine. Whoever's grading my work, they can guess what VC is if it's clear. There's nothing else. Okay, you can see why this is a multi-step thing, right? All right, so first of all, ask yourself, would this collision, right? We have one collision and sort of one conservation of energy kind of situation going there. Is this collision elastic or inelastic? Well, like I said, if things start to combine together or they split apart, then it's inelastic. So this is combining together. It's an inelastic example. So in some sense, it's easier because there's only conservation of momentum to worry about. So we'll do conservation of momentum from step 1 to step 2. Okay, so I'm going to write out the momentum in step 1. So it's P bullet in step 1 plus the momentum of the wood in step 1 should equals to the momentum combined in step 2. Okay, so this is conservation of momentum. Is this 1 dimension or 2 dimension? From step 1 to step 2, this is purely in 1 dimension. Okay, so here it's a little bit of a 2-dimension situation, but just comparing 1 and 2, it's purely 1 dimension. Okay, so we're going to be given these things. Okay, so we're given everything in situation 1 or time 1, and we want to find out h. This is our ultimate goal. As an intermediate step, maybe we want to find out the combined. All right, so we'll see what happens. Okay, so let's write this out. If you, again, this is a general skill. If you don't know where to go, just use the definitions. So write out the laws that you know this is a good starting point, and then use the definitions. And because definitions are always true, so you can always replace that with definitions and see what happens, right? So m bullet, ub, right? That's the velocity. That's the momentum of this guy. What's the momentum of this guy? Well, I can apply the definition, but I can be smart, right? Let's just say that's 0 because the velocity is 0, the initial velocity is 0. So we can just go ahead with that. And that's okay because of how I present it. Everything is very traceable, right? Traceability is a good, traceability is an important thing in getting points and writing professional work and getting points in exams. So it's all one and the same. Combined over here. So I need the m times v, but this time I need the m. So I'm going to say let capital M equals mb plus mw, like this. Okay, so this is going to be mb combined, right? So it's like m combined, b combined, like this. Okay, yeah, I'll match that up as well, just to be clear, right? So at point 2, I think we won't collide because this is v, this is u. So there's no collision of variables. That's good. All right, what do we know? Let's check off things we know, right? So now you go and take a different pen and yeah, let's take a blue pen and go, hey, normally I'm given this, so I know this, I know this, right? I'm also given MB and this, so I will know this. Okay, so this actually tells me what V combined is, all right? So let's write that down. So it tells me V combined is, I say at some point I'll be lazy and make that VC. It haven't happened yet, but at some point it will. So that's fine because as long as things are traceable, that's really your primary concern, right? Okay, so make that a subject. So isolate that, right? So you have MB U B, U of bullet, divide by M. Let's actually substitute in here. So I have MB plus W. All right, good. All right, so that's the V combined. How is this going to go to this? What's going to happen? Is this a collision problem or is it a kinematics problem? It's no longer a collision problem, right? It's purely kinematics. So you can use the force approach or the energy approach. Which one's easier? Well, force approach, you have to resolve what the force of the bullet is. You could do that. However, energy approach is it's always easier. It's unclear what the force is. You can go and derive the force from the momentum. But yeah, let's just go with energy and compare point 2 and point 3. Okay, so I'm going to use conservation of energy from point 2 to point 3. So that means the energy total in point 2 should equals to the energy total in point 3. What's the energy total over here? Well, there can be kinetic at point 2 plus potential. And also we need to assume no heat loss and all that kind of thing from here to here. So energy is conserved over here. It's not conserved in 1 and 2 because that's inelastic. So there will be heat loss. This guy will warm up a little bit. But from 2 to 3, no additional heat loss happens from 2 to 3. Okay, so kinetic 3 plus U3. Okay, so U means I need to set my height. I'm going to set my height over here as h equals to 0. So at this point, there is no gravitational potential energy. and here it's going to just be mgh, okay? And at the maximum point over here, it better has 0 kinetic energy, right? So we're going to set that to 0. Okay, so we just have half mvc squared. Okay, so notice how I'm writing my work. Halfway through, I'm going to be lazy, right? So this just going to become VC, but I think it's clear to whoever's reading this what this is. If they follow through the work, there's only one logical choice over here. Same as M at some point, even though I wrote M combined here and combine at some point, there's only one logical choice what capital M is, right? I make a deliberate, I didn't just write half mv squared, that's bad. Because what M is this little m stands for. V, you can sort of argue that there's only one V, but this M really, there is no good obvious choice. Is it the capital M? Is it the little mb or little mw, right? So I made a deliberate choice. The fact that whoever's reading my work sees that I made a deliberate choice to use capital M, not just the generic half mv squared. That only can refer to this. VC, again, I made a deliberate choice of putting C. It looks like that's the only logical choice. Okay, so over here, again, MGH, but use the correct variables. H is defined over here, that's fine. This is H is 0, so over here, that's the additional height. G is a constant, and I use the deliberate choice of M. Notice the M cancels, and what's my goal, right? My goal is to solve for H, and do I know everything else? I do. All right, so that's good. And we have solved, is this nice or complicated formula? Let's see. So if I divide over here, I have VC squared over 2G, right? Let's plug that in, all right? So I have 1 over 2G, and then we have MB over MB plus MW squared and UB squared. So that's the heights. Okay. Okay, good. So just quickly check if that makes sense. Let's see. So yeah, I think that makes sense to me. Okay, so good. All right. What that means is if I know the velocity over here, I'll know what height it goes up. All right. So you can, if you go and this is something you can see, one can go into the woods and actually try this out. If you just need to measure the mass, and then you can test if all these theories are correct. Now, also a good practical thing, you might also sometimes ask, well, who cares about this? Can I actually make this useful in my life? Can I find out something interesting about new things that I don't know before? You can actually invert this. If you ask yourself, sometimes I like to ask myself, once I figure out a formula like this, what are the easiest thing? What is the hardest thing to measure in this case? Well, the masses, just go and put it on a scale. You can weigh it and measure that. G, I know, right? Is it easier to measure H or U? It's probably easier to measure H, right? You take a video you shoot a gun, take a video of this going up a certain amount, and at the maximum, just freeze your screen, measure the height. The harder thing is actually the velocity. So you can actually, excuse me, backwards engineer this, right? And reverse this and make U the initial velocity, the unknown. And now you can calculate, initially it's gonna be very hard to calculate how fast a bullet travels. But by shooting it onto a block and it moves it up, by measuring the height, you can actually predict what was the initial velocity of that bullet, okay? So, but let me just quickly invert this, right? So I need to multiply 2G over here. So I have 2GH, and then these are gonna go up as MB plus MW over MB. And I need to take a square root. So UB is going to be, the square is gonna go and going to be that, all right? So if everything here is known and I can measure H, I can actually predict how fast the gun is, all right? Another interesting effect you can learn from this is you now understand the idea of how recoils work. because if you shoot a gun, right? If you shoot a gun initially, what happens? So initially, there's no momentum. So this is before and after, right? The bullet is going out at some MV, right? So what's the total momentum after in the final stage? Well, the total momentum should be the momentum of the gun plus the momentum of the bullet. Initially, what's the total momentum? Nothing has happened, right? So it's 0. Is there any external force going from before to after? You might think there's a force pushing the bullet out, but that's internal, right? By external is there any force? Is there any force outside of the system? My system is the gun and the bullet, right? That's my system. So that's final. Let's make sure, right? So there's no external force other than that. Every force is internal within the system of gun plus bullet. So initially there's no momentum, and no external force means conservation of momentum will hold. So P total initial is 0. P for the final is that. So you see the P gun is going to be minus PB, P of bullet. So let's say the mass of gun is M, and this is little m, little mv, yeah, that's good enough. So mass of, so V bullet, let's call this. So we still have the gun over here, and you have the V of the gun, right, is equals to negative of M and V of the bullet. So what's the V of the gun? This is one dimension, so make sure, so the negative values mean going, this is positive going backwards like that, minus M over M of VB. Okay, so what do you learn? You see, first of all, this is negative, this is positive, 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 VB is positive. So V gun is negative, so you actually, this is the theory of recoil. And you see the faster the bullet shoots out, the more the recoil is. And the bigger the ratio of this, the more the recoil. So basically the heavier the bullet, the heavier the bullet, the more the velocity of the gun is negative, right? The more recoil. And the heavier the gun, the smaller the recoil. That makes sense, right? You have more inertia there. All right, so you can realize there's lots of use in physics, a lot of ways to, a lot of new things you can predict. You can learn a lot of new things. Hopefully, you see the theory of motion is full of variety, full of interesting things, the rest is just you getting familiar with the practice. And let me know if you have any questions. Otherwise, I'll see you in the final. This concludes part 4. I'll see you in the final part about objects. So far, everything is almost, I could approximate with the 0 dimension point, but then we'll finally consider the fact that in the real world, things are not concentrate, all the mass is not concentrated at the center of mass. Things have a size. What does the fact that things have a size will change to motions, right? The fact that things have extended degree of size, that got to have some effects on motion, and we'll look at that in part 5. All right, have a great weekend and see you next lecture.